In this video, I'm going to talk about dynamic memory allocation in C. Now, dynamic memory allocation is a tricky enough of a concept that I think it'd be good if we use some slides and go over some visualizations in addition to going over some code examples, just to help us wrap our heads around it. So to talk about dynamic memory allocation, we want to think about how memory works in C and understand how memory works in C. So with memory in C, our program is ultimately stored in what's called RAM, random access memory, and same thing with the variables in our program. And the variables in our program are all given some kind of memory address where that data for that variable is stored at. And our program basically references those locations like 2000, 2001, 2002, and so on. And there's usually some block of memory that's unused as well because our program doesn't take up all of memory. So there's actually two main ways in which memory is allocated and organized within C. There's the stack and there's the heap. So memory is effectively this ordered list of locations to store data. And the data is really just numbers at the end of the day. And each slot in memory, each position in memory has this unique sequential memory address. Sort of like how we've got like 1000 Main Street, 1001 Main Street, 1002 Main Street. Same thing with memory addresses. Regular variables are stored on the stack. So the stack is what you've probably been using so far without thinking of it. So when you make regular variables in C and you declare them and you have like parameters inside your function, those variables end up on what's called the stack. And that's in contrast to the heap where dynamic memory allocation takes place. So that's why we want to talk about the stack first, understand what's going on there so we can understand the heap and what's different about it. So as our program needs more memory for variables, the data gets stacked in order right next to the existing memory that's already allocated for existing variables. And that's basically the stack. So if you've got a program like this is a simple example here, it's a simplified example, but let's say we've got this main function here that has variables A and B. It declares variables A and B. Well, those variables will be declared on the stack. Now, when the main function calls my function, and my function has parameters, which are basically local variables, int C and int D, then those variables are going to be on the stack. So you're going to have C and D on the stack as well. And that's why we call it a stack, because A and B were needed first and created first, so they end up on the stack first. Then when main calls my function, then C and D end up on the stack next. Now when this function returns and C and D are no longer needed, then those variables basically get peeled off the stack and the stack rolls back to essentially ending at B there. And that's how the stack works. Now, there's a couple things about the stack that make it different than the heap. So the stack is ordered and all the data on the stack has a fixed size that doesn't change. So like a float variable will take up 4 bytes and a double will take up 8 bytes. That might vary a little bit from one computer to the next, but that's basically the idea. And arrays will take up the size of the type multiplied by the number of elements of that type. So if you have like a float array of size 10, then each float would be 4 bytes and all of those 10 elements would be 4 bytes each. So 4 times 10 would be 40 bytes. And those things on the stack, they have a fixed size that doesn't change. That's in contrast to the heap. Things on the heap can have different sizes and they can even have their size changed as well. So exactly when and what order things are placed on the stack depends on how functions are called and when they return. So, if my function here called another function and that function had, its own local variables, then those variables will be placed on the stack next. So things kind of get stacked in order with a stack. With the heap, it's not like that. With the heap, things are going to be a little bit more ad hoc, a little bit more less ordered than that. So when a function is called, its local variables are placed on the stack, and when it returns, they're removed. There's technically more going on with the stack than that. Technically speaking, there's places on the stack to store the return value, but we don't really have to think about that necessarily to understand what's going on here. So the heap is for dynamic allocation of memory. On the heap, we can request blocks of memory that are different sizes at runtime, and we can also resize those blocks at runtime. And what we're going to do is we're going to have a pointer variable that keeps the memory address of that block of memory on the heap that's been allocated for us. And the blocks of data on the heap, they can be different sizes, and they're not necessarily on there in the same sort of order as they would be on the stack, where things on the stack are created in the order they're needed. On the heap, we can actually kind of programmatically control when we free up space and when we allocate space. And so there isn't really the same sort of order to it. It's much more ad hoc. It's much more dependent on how our program decides to use the heap. So malloc is a function we can use to request a block of data on the heap, a block of memory on the heap. And there's another function too called calloc. They work just slightly differently. But malloc allows us to, say, for example, create a dynamic array of elements by requesting space for the number of elements multiplied by the size of each element. So what malloc accepts as an argument is the number of bytes for this block on the heap that we want to allocate space for. And what malloc returns is a pointer, a memory address to that block of memory. And that pointer is basically typeless. It could be really any type, and we're just going to, assign it to some pointer so that way we can then reference that data as we like, as an int, as a float, or whatever. And we're actually going to use this size of type to help us work with malloc. So let's go over an example of using malloc here. I could make a pointer like this, int star a, and I can then have this pointer set to point to a block of allocated space on the heap. So I can say is equal to, and I'm going to say malloc. And what malloc expects as an argument is the number of bytes on the heap to allocate space for. And what it's going to return is a memory address to that space. And a is going to be a pointer that's going to hold that memory address. So here I'm going to say size of int times 10. And what this is going to do is it's going to allocate space for 10 integers on the heap. Now we say size of int here because this is actually going to return how many bytes an int takes up on this system, essentially. So different computers can technically, and different compilers can technically store ints with different sizes. So you could have maybe like 8 bytes to store an int, depending on the system. As a practical matter, it's almost always 4 bytes, but we say size of int because we technically don't know. And so this will return, the size to store an integer, and then we say times 10. So we're basically allocating space for 10 integers then. And we call this a dynamically allocated array. And we call it a dynamically allocated array because we can actually access this like an array now. We can treat it like an array. So what I could do is this. I could say like for int I is equal to 0, I is less than 10, I plus plus, I'm going to say a at I is equal to 10 minus I. And what I'm doing now is I'm accessing the block of memory as if it's an array using what's called array notation. And I'm accessing that block of memory and I'm accessing each element in that block now as an array element because we can do that. This is the array syntax it's called. It allows us to access it like it's an array, which is a pretty typical thing to do with this kind of memory. And we're going to say here a at I is equal to 10 minus I. I could also then print out the data after I've set it too. So I could say I is less than 10 here, I plus plus, and I'm going to print out that data. I'm going to say printf a %d is equal to %d, and we'll just print out the data in that block of memory there now. And then one more thing I'm going to do is remember that ultimately what a is storing is a memory address. So if I did like a printf here and I said printf %, we'll say a colon %p, I can print out the memory address that is stored in a. And that's going to be the space on the heap that we're accessing when we access it like this and we print it out like this. That's the memory address of the space on the heap that malloc has allocated for us. So let's just run this and see what happens so far. So, and I'm missing some important things here, but that's okay. We can get to that. Okay. Oh, you know what I forgot to do? This is very important. So when you want to use malloc, you have to include stdlib.h. So stdlib.h, that is the library that includes malloc. So whenever you want to use malloc, you have to include stdlib.h. So we'll just give this a clear and then a recompile. And we run it here, and I get A0 is 10, A1 is 9, all the way down to A9 is 1, which is what I expected based on how I set them. And you can see that A is this memory address to this block of data here that we're now using like an array and storing different things in it. And this is what we call a dynamically allocated array, and this would be a typical use case of malloc. Now, one thing that's very important when we use dynamically allocated blocks of memory like this is we have to remember to free the data when we're done with it. We have to remember to free the space when we're done with it. And that's very important because with the stack, that basically happens for us automatically. Like when we call a function, that function has some variables in it, and then the function is done, the stack just sort of automatically retracts to where it was before that function call, and we don't have to worry about that space anymore. With this here, once we've allocated space for this dynamically allocated array here, if we don't free the space up, nothing else can use it. So if we don't free the space up, it's kind of gone. So I'm going to say here free A. And what this does is not going to actually impact the ability of our program to run in this case because it's a simple program here. But what that does do is it basically allows the space that this memory address here is pointing to be used again. And once we say free A, we're basically done with the space, and our program no longer controls that space. Like our program no longer, it's technically possible for our program to access that space, but our program no longer controls that space, let's say. So that's a very important thing with dynamic memory allocation is that we have to remember to free the space when we're done with it. Now, just so you know where the heap is, the stack grows downwards like this into the unused memory. The heap kind of starts at the bottom of memory, we can think of it as, and it grows upwards into the unused space. So the heap, one thing we got to worry about with the heap potentially is, technically speaking, it could become full. So technically speaking, we could allocate so much memory that the heap becomes full. And so it's very important, again, that we free space when we're done with it, so that way it doesn't become full, because we don't have the situation we have with the stack where it's going to be freed up automatically for us. So we got to worry about memory leaks as well. And memory leaks are basically where one of the ways a memory leak can occur is where we forget to free the space. So we forget to free the space, and maybe we don't have a pointer to it anymore. And now all of a sudden this space can no longer be allocated, and we can't free it anymore. And it's just what we call a memory leak at that point. It's kind of memory that's basically lost at that point. And so that's something we have to be concerned about. So in C, the fact that we have to manually call free to free up space like this, and the fact that we're having to manually manage memory by requesting a certain block of size, we call that manual memory management. And manual memory management is actually quite powerful in the sense that we as the programmer control completely how we're using memory. But it's also a little bit dangerous in the sense that we can make mistakes. So we can forget to free the memory, and we can have a memory leak. So it's a nice power, but it comes with responsibility here. So a memory leak can occur if we fail to free the dynamically allocated memory. And that means the space is no longer available for our program to use, and our program might not even have access to it anymore if we don't have a pointer referencing that space. And we can have very slow performance as a result, and we can have the sorts of errors that are very hard to detect. So we can have errors that are very hard to detect because of this. So a slow memory leak can be very difficult to detect. There's some other things that can go wrong with manual memory management too. So pointers might exist to memory that's already been freed. The program may attempt to free memory that has already been freed. So we have to worry about these things as well when we do manual memory management. So let's actually do an example of a memory leak occurring. Let's say that I am going to say here, I'll say /* / here. And what I'm going to do is I'm going to make a function that's going to just that's just going to allocate a block of memory. So I'll call it here like void. I'll call it like memory hog. And what it'll do is it'll take in some size here, and it's going to allocate space on the heap for things, but it's not going to free it. So it's just going to allocate space for things on the heap, but it's not going to free it. And it'll allocate space of size. So we're going to say here like int *a is equal to malloc, and it'll say malloc things of the size we give this function. And it's just going to allocate the space, and it's not going to call free to free things up. And then what I'll do is I'll have some code in my main function here that's going to call the memory hog indefinitely. I'll actually make an infinite loop. I'm going to say here while 1, I'm going to say call memory hog. So what I've got here, and I could even just put this on one line here, I suppose, but what I've got here now is a function that's just going to continually allocate space for things, but it's never going to give the space back. And now I'm going to repeatedly call the function forever in this infinite loop. And I'm going to request fairly large chunks of space. I'm going to request like, let's say like 1,000,000 bytes. So 1,000,000 bytes again and again and again and again forever, with it never freeing the space. What's going to happen is my heap is going to keep growing there into my unused space. So the data on my heap is going to keep on like gobbling up more and more of this unused space here in the middle, up until we get to a point where there's just no more space left, and the program should probably crash at that point. So let's see what happens. This will be interesting. A nice little experiment for us to do here. So I'll clear this here, and I'm actually going to reduce this to, we'll say 128,000. I think that's a little, I think 1,000,000 might be a little too much for it here. And we'll compile it here and run it here. Now, when I pull up what's called the activity monitor, this should let me see the program eventually take up more memory than we've got here. So if I leave this running for long enough, eventually what should happen is the program should just take up more memory than we've got. Because what's happening here is it's repeatedly calling memory hog. Memory hog is repeatedly trying to get memory of this size, and it's never freeing it. And so our program should just take up more and more memory until it eventually makes it so that our computer just has no more memory, or there's no more memory that can be allocated. So I'm just going through the activity monitor to see if I can see the program. So there it is there. There's D. It's running there. And if we see maybe this is under CPU. If I go to memory here, let's see if I can see D. Oh yeah, look at D. That's D there, and it says, I can't really make it bigger, unfortunately, but it says there 1.99 gigabytes. So D is just taking up way too much space. It's just going to keep growing, right? And eventually what should happen is our program should crash with some kind of error here. Oh, 3.25 gigabytes, 5.17 gigabytes. So eventually our program will crash because we're just continuously forever allocating more and more memory, but we're never actually freeing it. And eventually our program will crash. I'm not sure if we want to leave it running here until it does, but I'm hoping it'll happen any second now, but maybe not. Maybe we won't get that lucky. So I'll just leave it running while we keep talking about this stuff then anyways. So, because we can see it crash there on the side when it does. Oh, there it says, killed 9. So there it goes. It just crashed there. So this is what we can't do. We can't just sort of allocate memory forever like this without freeing it. Eventually our program will crash. It'll run out of memory. And so we have to be mindful of that. So I'm actually going to just temporarily not do this just because we don't want our program to crash. And let's just go over a couple more ideas here. So one thing we've got as well, in addition to malloc, is another function called calloc. And the way calloc works is pretty similar. You just say calloc, and then you give here, we're just going to say calloc, open bracket, and you give the number of things and then the size of the things. So you'd say like 10, and then you'd say like size of int. And then this will declare space for 10 integers here when we do that. So it gives space for 10 integers here when we do this. So why use calloc instead of malloc? There's another video that I've posted just comparing calloc and malloc. But what calloc does is it zeroes the space first. So calloc will set the space to all zeros when it gives you the pointer back to it. Malloc doesn't do that. Malloc will just keep whatever junk is in the space. And that's a big difference between malloc and calloc. So this will work remarkably the same to what we had before, where you're still going to have like A010, A91. The only difference is that before we set these values, it was guaranteed that all of the memory allocated in this block here was zeroed. Now, for some reason, calloc is called slightly differently too. You call it with like the number of things and then the size of those things. So like 10 and then size of integers. That's one difference as well. So one of the reasons why we might want to use calloc is if we've got a long running program, the program's been running for like a long time, and we've been allocating space and freeing space and allocating space and freeing space, calloc might be important because maybe we need to guarantee the space is zeroed. Because when we call free is not going to delete the things in the space and set it to 0. When I call free A, that space is still going to be populated with whatever was there before. So let's actually, before we call free A, I'm going to maintain a pointer to A. I'm going to say here like int star save, and I'm going to set it equal to A. Then I'm going to free A. What that's going to do is it's going to make it so that my program essentially doesn't control the block of memory that's been allocated at the memory address A. But what I'm going to do though for fun is let's see what happens if we printf what is at A, what is at that memory address, because I've actually saved it. I've saved the pointer to A. I've got the memory address A stored. And if I were to do a printf of save, we're going to see that save stores the same value that A had before because I saved A's value in save. And what I'm going to do now is I'm going to do a printf of the values at save. And we're going to see what is at save, the data, the block that was previously set aside that we've been using as a dynamically allocated array so far. So if I run this here, we're going to see that save has the same memory address that's stored in A. So save is storing the same memory address that A stored, which makes sense because we just assigned it to it. But when I call free A, that frees up that block of memory so that it could be allocated again. It means that other calls to calloc and malloc could use that space. But what it doesn't do is it doesn't delete the data in that space. So this block of memory here, it still has like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 stored in it. And that's something we really need to be aware of when we use dynamically allocated memory, is that when we free it, it just makes it available to be allocated again. It doesn't like set it to 0 or, quote unquote blank or something like that again. And that's important for a couple of reasons. Number one, that's why we might use calloc, because calloc will guarantee that if somehow we get this space again, it is set to zeros. That's why we use calloc. Now, the other thing that we got to be aware of is, let's say that I was storing a password in my dynamically allocated data, and then I said free that space. The password would still be in memory, and that could potentially be a security risk. So we got to be aware of that as well. Now, another thing I can show you with dynamic memory allocation that's important, and I've actually posted another video just on this, is another thing we can do with dynamically allocated memory is we can reallocate space for larger blocks, for a larger block of memory. So the size of the space that we allocated is not fixed. We can actually use realloc, another function, to increase the size of it. And I've actually posted a video just on realloc and just going over the ins and outs of it, but I'll show you the basics of it here. So here, what I'm doing is I'm saying int star A calloc is set to 10. And like one of the nice things I can do with dynamically allocated memory is I can very easily change 10. I could even make it some variable. So I can make it so that like I say printf and I say like enter size, and then we're going to do scanf here, and I'm going to store the size that is entered into a variable called size. So I'll say like int size 0, and I'm going to ask the user for a size. Then I'm going to store the size that they enter, some integer, into size. And I could use size to actually allocate space and set up my data. So here I'm actually going to use the variable size now to determine how much I allocate and how I set it and how much I print. And this isn't going to be too surprising. If I run this here and I say like size 2, I've got like A02, A11, and so forth. I could say like 5, and I get that. Now, that's one cool thing with dynamically allocated memory is I can very easily do this. Now, in the newer versions of C, you can actually create an array with a size that has a variable. So you can actually use like a variable to create an array of different sizes at runtime. You can do that in the newer standards of C, like C99. The older versions of C, you couldn't do that. Now, the one thing though you got with dynamically allocated memory is you can even resize it after it's been allocated. So you can use what's called realloc to say, I want a bigger chunk of memory now. And so what I'll do here is, after I've already used this piece of data here, what I'm going to say, and I should say free A here, but what I'm going to do is after I've allocated this space, I'm going to use realloc to allocate more space. So I'm going to say here A is equal to realloc. And realloc works a little bit more like calloc, where you say, or like malloc in the sense that you just give the size, but you give it as the first argument, you give the pointer to the space, And the second argument here, you give the size you want to allocate. And what realloc does is it returns a pointer to the newly allocated block of space. And here you give it to the pointer to the existing allocated block of space. And as the second argument, you give the size of the space, the size of the new space that you want. So here I could say like size of int, and I'm going to say times, and I'm going to say size plus 5. So what I'm going to do is whatever size is entered here, maybe it's 2, maybe it's 5, whatever it is, I'm going to say use realloc and say that block of memory that we've got at position A, at memory address A, I want more. So I want to take that memory address, I want to take that memory block, and I want to increase it by size plus 5. So like take whatever the size is, add 5 to it, multiply that by the size of an integer, and give me space to store that many things. And then what realloc does is it returns a pointer to that new block of memory. And that new block of memory is going to actually contain the same old values that were stored in the old block of memory, but it's also going to contain space to store new pieces of data as well. So what I could do is, because I've increased it by size 5, I could say, okay, let's put in those additional 5 spots the value 9. So I'm going to go from I being size up until I is still less than size plus 5. And at those extra 5 spots, let's put the value 9 specifically. And then I'm going to do a printf, and I'll do a printf that's going to go not just until size, it's going to go until size plus 5. And what I've done is I've basically just gotten a bigger block of memory by, 5 by up to 5 more spaces here. And I'm going to store 5 more values in there that are all going to be 9s. And I'm going to do a printf just to show that I've stored all 9s at those last 5 spots there. So let's just run this here, and we'll do a recompile here and run this. And I'll say 5, I'll say 2. And I get like A0 is 2, A1 is 1, and then I do a realloc. And now I've got A0, 2, A1, 1, and I have in the last 5 positions, 999 that I've stored there. And I've increased the size of this thing by 5 integers. And that's a cool thing that we can do with dynamically allocated memory as well, is that we can actually change the size of the block of memory that we've allocated for things to. So I could just run this one more time. I could say 5, and it's a very similar thing here. We've got like, 5 to 1 stored in these 5 positions in our dynamically allocated array of size 5. But then I've increased the size of it by 5. And in those last 5 spots there, I've stored, 5 9s there. And that's just another cool thing we can do with dynamically allocated memory is we can reallocate more space. And like I said, I posted a video just on that, just to go over the ins and outs of how that works, because some of the specifics are kind of cool there. So with C and this manual memory management that we're doing, we have to be aware that this is coming at the benefit of performance, but it's coming at the cost of more responsibility as a programmer. So we have to manually remember to free the space we've allocated. And it turns out that programmers in general are not so great at doing that. We forget, and we can't help it, or we just make a mistake in our logic and we just can't help it. So most languages nowadays that are more recent in terms of their creation, C is a very, very old language in comparison. It's kind of like the great-great-grandparent of a lot of languages. Most modern languages don't have this sort of manual memory management. C is also what's called a systems language, where it's intended for really low-level use cases. That's one of the reasons why it allows you to have this much control and this much power over things. A lot of the more modern languages are intended more for application development, where you're making like maybe some kind of database-driven application for some kind of business client, something like that. And so they don't want programmers worrying about things they don't have to. And most modern languages go with a different technique. So the fact that memory leaks occur in a language like C, that's kind of a criticism that some people would have of the language. Really, it's more of a best tool for the job situation where, you're going for what different things, right? Different programming languages provide different values. And C's is high performance because you have total control. Now, part of the reason why the sort of automated memory management comes at a cost is what's called garbage collection. So if you're using a language, say like Python or Java, they have what's called a garbage collector. And what they basically have is a process. They have a process that runs alongside your program called the garbage collector. And in the case of Python and Java, your program is running in essentially a virtual machine that is running your program. And the garbage collector is basically this additional process that runs. And what it does is it periodically checks the heap for blocks of memory that are no longer being used, and then it frees them up. So if your Python program or your Java program no longer has a variable referencing a piece of data, then it's considered that you are done with that piece of data, that there's no variables referencing the piece of data, so the programmer must be done with it. The program must be done with it. And if that's the case, the garbage collector says, okay, time to clean up this data, and it does it for you. And so it basically kind of detects these chunks of memory that are no longer being used and frees them up for you. Now, the fact that that process has to run alongside your process is one of the reasons why these languages can be slower. Now, modern garbage collectors are extremely fast. So modern garbage collectors are extremely good compared to when they first sort of arrived, maybe 25 years ago or so. So the additional process, it does slow performance, but nowadays it's not really a big hit compared to what it was before. And I mean, I don't know, I might be being controversial or something like that. If somebody's really got like a good handle on these things, I might want to kind of say, well, really, maybe there is still a difference here and there. But even still, like, this is part of why C is considered a lot faster than Python and Java and languages like that. And that's a big reason as to why. But it does come at the cost of that responsibility. So just be aware of that. Check out portfoliocourses.com, where we'll help you build a portfolio that will impress employers, including courses to help you develop C programming projects.